So, yeah. Hello everyone. I am very happy to be here in the third online Vedic Math conference, and it was wonderful listening to all of the presenters today. So, Swati, how much time do I have?
Take your time. It's okay.
Okay.
How long do you think it would be? 20 minutes?
20 minutes? Yeah, I think 20 minutes.
Perfect. No issues. Take it.
I have around 21 slides, and I'm motivated by Ken's presentation. 20 divided by 21. How much time should I spend on one slide? So it was wonderful listening to all the presentations till now. I think one of the common aspects that we saw in all the presentations is that everybody is trying to see this struggle for learning math in different countries.
Recording started.
Okay, so as we all see this kind of struggle that students face in math, in different countries, I think the levels are different and the struggles that they face are different. I just want to share some examples and some pedagogical aspects that I have tried with students in India, and how it has created the sessions a little more interesting. So I've used two things. One is puzzles and the other is proofs, because puzzles is something that everybody loves to solve. I mean that even for somebody who's not very good at math would love to solve some puzzle. And proofs is something that really helps us to ascertain whether we are right or wrong. So we'll look at what I intend to cover in puzzles and proofs in the next few slides. So here is just a small slide of Ekadhikena Purvena. I'm assuming that everybody knows this technique, Ekadhikena Purvena, but just for the sake of in case anybody who's not introduced to Vedic math, I'll just explain this. So here we can see we are multiplying two two-digit numbers, 23 times 27, let's say, and the condition for using Ekadhikena Purvana is that the units place digits should add up to 10. Like here, this 3 and 7, it should add up to 10, and these 2's, that is a tens place digits, or even if it's a 3-digit number, whatever is the remaining part, those two parts should be the same. So what we do is Ekadhikena, that is one more than the previous. So this is the last digit, this is the previous digit. You do 2 times 3, you get 6. 3 and 7 you multiply, you get 21. So that is what we do for Ekadhikena Purvana. Now generally when we do this, in fact I had shared a bit about this in the first online conference where I spoke just about puzzles and how puzzles can make a classroom of Vedic math interesting. So here I just want to extend it a bit ahead. So let's say that once we have done Ekadhikena Purvana in a particular class, then we can give this kind of puzzle, like multiplication of two two-digit numbers gives me 3016, 7209, and 11021 and 13224. So here are 4 examples. Can we figure out what are the two-digit numbers? So especially once we do it immediately after Ekadhikena Purvana, I think it's not very difficult for students to kind of figure it out. Of course, when it goes to 5-digit numbers or more, it might take a little more time, but again they would be happy because this is a puzzle. It's not a direct question where we just give 2 numbers and ask them to find the answer. So I think this is one way of even testing if the student has got the technique very well, instead of just giving 2 numbers. Or this can be in fact in when we conduct online exams, many a times we get this we give questions, like for example when I do an online course on Vedic maths, if I give a question, what is 23 times 27, how do I know that the student has not used a calculator at his end to get the answer? But if I give it in this way, then even if they use a calculator, it's going to take quite a lot of time. So this is one good way for me to test whether the student has really understood what is Ekadhikena Purvana. Yeah. So this is one kind of puzzle that we can do using Ekadhikena Purvana. Another kind of puzzle that I really like is combinatorial puzzles. So here's one example. That is if we are having a 2-digit number like A5 and the other one is A5. So A5 multiplied by A5 is BCCD, let's say. So what I mean by A5 is it's a 2-digit number that is ending with 5, and BCCD is a 4-digit number. And since A, B, C, D are all different alphabets, each of them represent different digits. Now when we see this, a student who has done Ekadikena Purvana and who has understood, maybe he'll see this very clearly, that the tens place digits are same and the units place digit, they add up to 10, so we can definitely use Ekadikena Purvana. And from that, from 5 and 5, we can get the value of C and D, which is 25. And then we see C, there are 2 C's, so that it should be something, B 2 2 5. So we just need to find out A times what number gives me BC, where C is 2. Now the question is not to find one solution, the question is how many solutions exist. Yeah. So this can be a very interesting problem for middle school students, because they don't come across combinatorial questions in middle school. They just learn questions where there is one question and there is one solution. But now here they have a question which has got many solutions, and they have to find how many solutions exist. So let's say that they come out with, somebody comes up with 1 solution or 2 solutions or 3 solutions. So the next question can be, can we prove that there are only these many number of solutions? So then they'll start thinking, oh, I think that there are 2 solutions, but how do I prove that there is no third solution possible? Then we can encourage them to come up with different arguments why they feel that there are only these many number of solutions for this puzzle. So I'm just going to go through these puzzles. I'm not going to give away the answers. I just don't want to take out the fun in case anybody would like to take up these puzzles and solve. So the next one is, how many solutions exist for the below puzzle, that is 1224. So again, surprisingly, this is of the form BCCD, right, where the middle 2 digits are the same, but it does not fit into A5 into A5. So this once we have done Ekadikena Purvana, the student might think that, okay, so it's ending with 24, so the product of the units place digits have to be 24. So 8 times 3, 6 times 4, there are 2 possibilities, but then 8 plus 3 is not 10, so it does not work for Ekadikena Purvana. And if it has to work for Ekadikena Purvana, then it has to be ending with 6 and ending with 4. So both the numbers are ending with 6 and 4. Now we just need to figure out what is the tens place digit of both the numbers. Then we look at 12, and then which number multiplied by the next number. So product of which 2 consecutive numbers is 12. And then we can easily find out that it's 3. So 3 it will be 36 and 34. I know that I just gave away the answer for or one solution for this particular puzzle, but I just wanted to show that what might be the thinking process involved while we are solving this puzzle. So the student will be forced to think and come out with different reasons why it has to be 36 times 34. But then how many solutions exist for this puzzle? So what happened was, I'll tell you how I got this particular question. So the first question I still remember was, product of 2 2-digit numbers is 1089. I had just given that question in the class, and then 2 students came up with 2 different answers. Of course, one is 33 square and the other is 99 times 11. So I was trying to ask them that, can you prove that there are only 2 solutions, and which they really liked. And this was a group of 6th graders, and they did not know much of algebra, but then they could come up with reasons that why only 2 solutions exist. So these kind of puzzles we can form using Ekadikena Purvana and even the other techniques. So this is just an example that I have taken to show for a combinatorial puzzle using Ekadikena Purvana. This one is one of my favorites, that is 99 times 91 is 9009. So when we do multiplication, sometimes we come across palindromes, and it is always interesting to find, how many such palindromes exist. So palindromes itself, how many palindromes exist is how many 3-digit palindromes, how many 4-digit palindromes exist. It comes under combinatorics. Again, it can be a combinatorial question, but here we are talking about some specific calculations, that is 99 and 91, both of them, they come under Ekadikena Purvana if you do 99 times 91. And product of 2 numbers which come under Ekadikena Purvana is giving me a palindrome. Now I'm interested in finding how many such pairs of 2-digit numbers exist whose product will always be a palindrome? So I posed this question to a group of students, and I was really surprised. I mean, I had thought of of one normal way, a non-algebraic way, and a very logical way of arriving at the answer of why n number of solutions will exist for this particular question. But I was really surprised to see one student coming up with an algebraic way, and the other one coming up using a mod function, and then he proved that why only these many number of solutions exist. So both these things were, it did not occur to me that we could actually do it. So these kind of puzzles, I think, will create a lot of exploration, or what we can say, a flair for exploration in students. Okay. So this is Nikhilam Sutra, that is, if we have to find Nikhilam of a number, that is 100 minus 65. What number is 100 minus 65? We can use Nikhilam Sutra. So this is one slide, and just to explain, it just says all from 9 and last from 10. So 9 minus 1 is 8, 9 minus 9 is 0, 9 minus 8 is 1, and last from 10. So 10 minus 2 is 8. And this is how we can find the Nikhilam, or the complement of a particular number from its next power of 10. So here the next power is 10,000. And these are some kind of puzzles that we can give for subtraction. I mean, subtraction, sometimes it looks very basic, but then we can ask them that, again, these are the type of questions that we can give to ensure that the student is not using a calculator when he is not in front of us. When it's an online exam, I can give this: find the Nikhilam of 5A6B2, which is a 5-digit number, and its Nikhilam is C1D4E. So find the values of A, B, C, D, and E. So for doing this, he can definitely not use a calculator, and this is a good way for me to check if the student has really understood this Nikhilam subtraction. Moving ahead, Ekanyunena Purvena. So I'll just skip explaining this one. Explaining the technique. So let's say that we have a 2-digit number multiplied by 99, and we need to know if if we are given product of two-digit numbers, and then we are given the answer, and we need to know what are these two-digit numbers. A student who has learned Ekanyunena Purvena will know that the sum of the first 2 digits and last 2 digits, it will add up to 99. So he'll say that, okay, so this adds up to 99. This, when you add 63 times 36 gives 99. 10 times 89, 10 plus 89 gives 99. But here, when we add this, it is not giving 99. So the one who has learned Ekanyunena Purvena will know that these three come under Ekanyunena Purvena, but this one does not come under Ekanyunena Purvena. Yeah. So again, when we know that this comes under Ekanyunena Purvena, can we find out what are the two digits? Of course, one would be 9, and the other one would be 99, and the other one we need to figure out. Again, this can be extended as a combinatorial puzzle, saying that given this answer, how many 2-digit numbers exist whose product will be 3960. So recently I posted a question in a webinar for which the students are still working on. That is, let's take the example of 1089. 1089 it can be written as 99 times 11 or 33 times 33 as product of two 2-digit numbers. Now I'm interested in finding a 4-digit number or let's say it can be a 3-digit number also, whose product is of two 2-digit numbers. That is, you multiply two 2-digit numbers and you get a 3-digit number or a 4-digit number. But you want to find out, can there be alternative ways? Like, for example, this 1089, it's a product of two 2-digit numbers, and it can be done in two different ways. Now I want to find a number which is a product of two 2-digit numbers, but it can be done in more than 2 ways. Let's say 3 ways or 4 ways or 5 ways. And I want to find a number which can be written as product of two 2-digit numbers in the maximum possible way. So can there can there be a number like 1089 which can be written as product of two digit numbers in maximum number of ways, and how can we prove that there is no other number which can be written as product of two digit numbers in more than that many number of ways? So these kind of puzzles I think would be very good for students who are really passionate about mathematics, but we can lower the level of puzzles and keep it very basic for the students who are just getting into Vedic Math. Like for example 6336, it can have how many it looks like a palindrome, and then we can see that it's coming under Ekan Union Apurvan also. So we can ask how many two digit numbers when multiplied by 99 gives us a palindrome. Again, that's a combinatorial problem. Yeah, so this is what I was talking about. So the last thing that I was saying was that how many 2 and 4 digit numbers exist which when multiplied by 99 and 9999 result in palindromes. So we know that 11 times 99 is not a palindrome, but we know that 55 times 99 gives us a palindrome. So how many two digit numbers exist like 55 which when multiplied by 99 gives us a palindrome? So how many, when it's a question of how many, we need to find out how many numbers exist, and the next question that we can ask them is, can you prove it using any logic or using algebra that only that many number of two digit numbers exist which when multiplied by 99 gives us a palindrome? Same for 9999. Yeah. In case you are wondering why I missed out 999, then maybe you can try that. Is there a 3-digit number which when multiplied by 999 and it gives us a palindrome? So if there is a number, how can we find the number? So because there are 900 3-digit numbers, it won't be practically possible to check out each and every number. So this is where proofs really come handy, that we can first check, is there such a possibility? If there should be such a possibility, what should be the relation between the 3 digits, that is A, B and C? Let's say ABC times 999 is a palindrome. Then what should be the relation between A, B and C so that ABC times 999 gives you a palindrome? And if there is no such number like ABC, how can we prove that there is no such number like ABC? So one student of 10th grade recently told me that, sir, I can't prove that there is no 3-digit number which when multiplied by 999 gives you a palindrome, but I can try to prove it by contradiction. I can say that let's assume that there exists a solution, and then I can prove that our assumption is wrong. So again, this is emphasizing. I mean, this would be like enforcing more on the proofs and encouraging the students to think and try to prove why they feel that this is only these many solutions would exist. So we are doing a few things at the same time. We are encouraging them to solve puzzles. We can even ask them to create puzzles of their own based on what we are doing in Vedic Math, and then we can try to extend it to some combinatorial puzzles, and then finally we can ask them, can we prove? So we are doing a lot of things by just doing a few numerical things. So it won't be just easy ways of multiplication, faster ways of multiplication. We are also looking ahead and going ahead with that. Another thing which I would like to encourage everybody is to work on proofs on sutras in Vedic mathematics, because as most of you might be knowing that this subject of Vedic mathematics is not very well accepted by some academicians, and the reason that they say is that it's just a bunch of tricks. I'm sure if they would take out some time and try to make an effort to prove each of the techniques, then they'll see that why it is not just a bunch of tricks, but it's an algebraic, there can be an algebraic proof to back every sutra. So here's one very simple sutra and very simple proof, that is of Ekadikena Purvena, that AB multiplied by AC, where B plus C is 10. So we can just expand it algebraically, and then we can see that why it works. Now it is very important, I feel, as mathematics teachers to come up with proofs, because I'm sure there would be at least some of you who would have got this question from students when you introduce them to such techniques which are applicable for special cases, and you say that, hey, this works for any 2-digit numbers that satisfy for ekadikena purvana, and they would ask, will it work for any 2-digit numbers that satisfy this pattern? How do we know? So they have this kind of curiosity that I know that 36 times 34, I can see that it's giving it's giving the answer using ekadikena purvana, but how can we be sure that any 2-digit numbers that satisfy these two conditions of tens place being same and units place being units place added up to 10, how can we be sure that all of them would give the answer using the method of ekadikena purvana? So there we can encourage them to come up with proofs, or if they are not able to come up with proofs, we can supply them with algebraic proofs or even numerical proofs. We can replace A, B and C with digits initially, and then we can take them to this kind of generalizations. I think if we can come up with proofs for all the sutras, that would be a great thing, because then we are we are presenting Vedic mathematics in a more authentic way. Authentic, I mean that authentic in the eyes of most mathematicians and academicians. So proofs there, I feel, is can be of dual benefit, that is finding out whether our technique is correct and then to get accepted in the Academy of Mathematicians. Okay, so coming to the last part, that is the test of divisibility. This is something that I do for students, especially who are preparing for competitive exams, finding the divisibility test of prime numbers, and of course it's very beautifully explained in Krishna Tirthaji's books. So here I'm just going to take one example, that is the case of 7. So if we have to find out if a number is divisible by 7, we take either the oscillator 5 or 2, and then we have two processes of doing it. We'll just go to the process. Most of you would be knowing this, but just for the sake of introduction, I'll just share it. Process for divisibility by 7 is, let's say if we are having a number 1498 and we want to check if this number is divisible by 7. So one way is we take the number 5, the oscillator 5, and we do 8 times 5 is 40. So we just add 40 to 49, that is 149. We are adding 40 to 49, and then we'll get 189, and then we just ignore this 8, the last digit. We take the units place of 9, and then we multiply it again with the oscillator. So the 9 times 5 is 45. We add 45 to the remaining part, that is 18. So 45 plus 18 is 63, and since 63 is divisible by 7, the entire number is divisible by 7. So here is just a small algorithm that I have written. We can stop this process anywhere. We can stop it at 189. We can stop it at the next step, that is 63. Wherever we know that the number is divisible by 7, we can just stop it. So this is one way of checking the divisibility by 7. The other way is by taking the oscillator 2. So before we so this is just the explanation. The next way is by taking the oscillator 2. So what we do is we take the units place 8, we multiply 8 by 16, and then 149, we subtract 149 minus 16, so we get 133. Again we take 3 and multiply by the oscillator 2, so 3 times 2 is 6, and we subtract 6 from 13, we get 7. So since 7 is divisible by 7, 1498 is divisible by 7. So these are two techniques that are seen for the divisibility test of 7 in Tirthaji's book. Now we can go to the algebraic part. So I have not taken algebra. I have just replaced alphabets with numbers just for the sake of quick understanding. So what we are doing when we are doing the divisibility test of 7 is that we are taking this 8. So I'm going by process 1 where we multiply 8 and 5, we get 40. So when we are adding 40 to 149 and we say that, ignore this digit 8. So what we are doing is we are actually doing 149, and then when we ignore the digit 8, we are considering the digit 0 and then add 40. So we are actually adding 400. So we are doing 1490 plus 400. And when we ignore 8, so what exactly we are doing, I think if I explain, I think it will be better here. So 1490 plus 400, this is what we are doing. And when we are doing this process, it was actually 1498 minus 8 because we subtracted this 8 and that's how we got this 0 and we added 400. So when we take this minus 8 plus 400, we get 392. So when we are saying you ignore the digit 8 and you add 40, what we are actually doing is we are taking 1498 and we are adding 392, and 392 is divisible by 7. So as Ken was saying in his presentation, if we add multiples of 7 to a particular number and at the end we are getting the final result as a multiple of 7, which means the original number is a multiple of 7. So that is the process that we are doing over here, and when we do it iteratively, here we are getting 1800, and here again it's the same process that we continue. So we can go on and then we will see that finally it will give this answer. So these kind of proofs, I think it would be very very good for students mainly who are really passionate about mathematics, and as mathematics teachers also it would be very good for us to come up with proofs like this. Okay, so the second process, I'll just the presentation will be available. I'll not go into much detail about the second part. The second part also, I think if you can try it out, you will get the answer, and then we can replace everything with variables, and instead of divisibility test for 7, if we check for 13 or something like that, we can see that also works with the same logic. Okay, so here's what I feel that each of these sutras, if we can try to prove algebraically, that would be a very good contribution from our end to the subject of Vedic mathematics, and that would be something more encouraging for students who are really bright in mathematics. And puzzles, we can use basic puzzles for students who are just getting introduced to Vedic mathematics, and that can create some more love for the subject. And creating puzzles is also a very good exercise for us, because we also start being creative. We are not just giving the routine type of questions to evaluate whether the student has understood or not. So towards the end of, let's say let's say that we cover 5 techniques in multiplication, and after, so instead of giving direct questions, maybe we can give a question and say that, okay, dash dash times dash dash is 2 3 4 5, let's say, and can we find the two digit numbers, and using which sutra can we find that, or using how many sutras can we find that, or how many solutions exist for this particular question. So the initial questions can be using which sutra can be just to understand that how much the student has understood whatever we have taught in the class. The second thing can be to identify very talented students who can come up with different ways of solving up with solutions for combinatorial puzzles. So I think with that I'll take a pause. I think I exceeded by some 3 minutes or so. I'm sorry for that. So we can take any questions in case you have anything to ask. Thank you so much.